Tension is classified as a response force. It's usually a force between two separate objects connected together by a string that's massless and infinitely strong. Reason for that is that we want to be able to transmit the force completely undiminished from object A onto object B. And if this string happened to have a mass, well, if you ever connected a boat to a shore before, you'll notice that the rope tends to do something weird like this, forming a curve known as a catenary. Alright, that just makes things way too complicated for our calculations. So we'll pretend that it's infinitely strong, has no mass so it doesn't droop, and from there we just start calculating everything out and predicting what the result of everything is. To make life simpler, we're going to treat everything as a scalar quantity. So we're going to assume that positive is the direction of acceleration of all the objects in the system. Ready for that? Let's get started. Alright, so let's say we have a system where Calvin wants to pull two wagons and Hobbes wants to jump in for the ride. Just to make things a little bit more unique and different between two objects, let's just say the first object has a mass of 10 kilograms and the second object, with Hobbes factored in, has a mass of 20 kilograms. Remember, this is a force-based problem, so we always need to include a free body diagram, and every single element needs to have its own coordinate system. Now in this setup over here, we can see that both objects are going to move to the right, so they'll both have a coordinate system where to the right is positive. Both objects are here on Earth, so they succumb to the force of gravity, but the ground itself provides a normal force holding it up. As for the mass that's on the left-hand side, the only reason why it's going to accelerate to the right is due to, that's right, tension. Rinse and repeat for the second object. Gravity's pulling it down. Normal force is holding it up. Calvin is trying to pull it towards the right. However, the tension force is pulling it in the opposite direction. Now that we have the free body diagrams done, let's create equations for each of these objects. Now, in this simplified problem over here, especially since mu k is equal to 0, there really is no need to calculate out for your f net y because it's going to equal to 0 and it really won't impact the rest of our answers. So instead, we're just going to focus on the x dimension. So when we look at the 10 kilogram mass, the only thing that's causing to accelerate is tension. So f net is equal to ma, but our f net is just equal to tension. So if these two qualities are true, then you can argue and say that ma is equal to tension. We now have an equation with two unknowns, so there's not much we can do, so we'll move on to the second object. Once again, in the y dimension, it's not necessary to calculate anything out here, so we'll just let it be. But in the x dimension, we can see that Fc is the positive direction of travel, tension is the negative direction of travel in the x dimension. So F net is equal to Fc subtract tension. F net is also equal to Newton's second law, which is ma. And really, if you wanted to start off with m2a is equal to Fc minus t, I'm fine with that as your very first statement. That's perfectly fine. However, when we sub everything in, we still have yet again an equation with two unknowns. So, two equations with two unknowns, what you going to do? That's right, substitute and solve. So, since the equation number 1 is already isolated for t, we can sub it into equation number 2. Just be careful. I think the most common mistake I see people make in the substitution is that they forget that there's a minus sign right here, and that minus sign needs to be distributed to everything that's equivalent to t. Okay, so just remember that you distribute that in. One other interesting thing is that in your second last calculation before your final answer, you'll always notice that the left-hand side equals the total mass. After all, F net is equal to total mass times acceleration. All right, so you shouldn't have a mass that's less than the total mass before your final statement. If there is, there's a good chance that you forgot a minus sign over here, and when you brought it over, that's when you ended up getting 10 kilograms times A. All right, so really just watch out for that part over there. 2 newtons per kilogram has the same meaning as 2 meters per second squared, and really that's it for these type of problems. Now, if you want to find out how much tension is there between the two objects, or how much tension is on the rope itself, then you'll just sub it into either equations 1 or 2. 2 seems more complicated, so obviously sub it into equation number 1. Crunch it through, and the strength of the rope needs to sustain at least 20 newtons, otherwise it'll snap during the acceleration. If this is summer school, then that's all you need to worry about today. However, in the regular school year, let's deal with even more interesting problems. Okay, so because Calvin loves wagons so much, he ended up getting another one just for kicks. There you go. So how are we going to solve this problem? And to make things a little bit more interesting, how about we factor in friction as well? Okay, so let's say that the friction on these systems is 0.1 for this kinetic friction. Why that value? I just chose an arbitrary value. That's it. All right. You have to look it up on the lookup table, like as you've seen in the previous episode. And this is usually the coefficient of friction expected between two slippery surfaces like wax on wax. Okay, 3 objects requiring 3 separate free body diagrams. Luckily for us, we know that all these 3 objects are moving towards the right, so that does make our calculations easier in a sense. You'll see what I mean in tomorrow's episode, all right? Okay, so all these 3 objects over here, they're all being pulled down due to gravity. Normal force is holding them all up. And this time around, we have to differentiate between the tensions. Okay, remember that forces always act in pairs. So in other words, a tension acting upon the 10 kilogram by the 15 kilogram is the same as the tension of the 15 kilogram acting on the 10 kilogram. So they're the same exact number here. And then there's another separate tension over here, and then there's the final tension right over here. And here's a question. What tension's acting on FC? Exactly. If Kelvin's pulling with a force of 60 newtons, then the tension on FC should be 60 newtons. Okay, let's get started on doing our calculations for this guy over here. But since there is friction involved, you have to think about logically where should the force of friction be pointing. And it always opposes the direction of motion. All right, now since friction does matter, we now have to deal with our F net in the y dimension, which is equal to the upward force of the normal force subtract all downward forces. In this case over here, it's the force of gravity of the first object. Now, this cart isn't going to float off into the sky, nor is it going to sink into the ground. So yes, F net y will go to 0. This tells us that Fn is equal to Fg, which is equal to mg. So 15 kilograms times 9.81 newtons per kilogram will give us a number. We also know that the force of friction is equal to mu k times Fn. So when we sub in our Fn, we have the force of friction to be equal to 0.1 times 15 kilograms times 19.81 newtons per kilogram, which will give us our answer that I've automated right over here. Okay, 14.7 newtons. It's not part of the PowerPoint because I expect you guys to know how to do all of that from last day's PowerPoint lesson. Okay, so if you haven't done yesterday's lesson yet, make sure you go through that first. Okay, now that we've calculated out the force of friction, we can move on to the x dimension. Tension's allowing to accelerate in the positive direction. Force of friction is holding it back. So T1 subtract 14.7 is equal to MA, or 15 kilograms. We're stuck. There's not much else we can do here because we have an equation with 2 unknowns. I'll just tell you that through practice, you're better off just isolating for T1 at this point here. Moving on to wagon number 2. As for wagon number 2, T2 is pulling it forwards, T1 and FF2 is pulling it backwards. Make sure you know how to calculate out your FF2, right, which would be, I think, 9.8 newtons. Yeah, 9.8 newtons. And you know that because you did your homework. You sub everything in, and you're left with this really messy looking formula. A formula with 3 unknowns. Your best bet is just to leave this equation alone. I know this from practice. Okay, moving on to wagon number 3. Can you think about it? F net's equal to? Good. Fc, subtract the force of friction, subtract tension. Please don't use this value here or this value here for your force of friction, simply because the mass is different. If they were all the same, then yeah, you could technically recycle that value. And you'll see that shortcut in tomorrow's episode. All right, so wagon 3 is equal to Fc subtract T2, subtract the newly calculated out FF3. I do recommend that in this formula over here that you isolate for T2. So you bring T2 over to the left-hand side, and you take this mass and you bring it over to the right-hand side, and that will become negative. 3 equations, lots of unknowns. What are you going to do? Sub and hope that you don't mess it up. All right, if you want to pause the video, then by all means pause it, work it out yourself. All right, here's the solution. So you sub in equations 1 and 3 into equation number 2, And as I mentioned, please watch out for this minus sign because this is the most common mistake I see in the solution, in the solving of this problem. Students distributing the minus sign into the first term, but completely forgetting to distribute it into the next term. All right, so please watch out for that. After you've carefully subbed it in, collected all like terms, it will simplify down to this for your acceleration. What about the corresponding tensions? I hope you figured it out. Take this, sub it into here, and take that and sub it into there to solve for the corresponding tensions of this connecting rod and that connecting rod. And once you've worked it out, hopefully you've worked it out too, those answers up there. For tonight's homework, here they are listed. And if you want to see the breakdown of this, then please by all means keep on watching the video, and I'll also take up the homework as well. All right, so here's the full solution of collecting like terms, simplifying, and solving. As mentioned, you'll notice in the second last step, your mass is always the total mass. If you get anything but that, it could be that you forgot to carry the minus sign through the terms or something like that. Okay, but your second last line before your solution is always the total mass. All right, what about the homework itself? Let's go through these. So you happen to own 2 toy ducks and you want to figure out what the acceleration of the system is. So because there's no friction involved in this first problem here, you don't need to worry about the y dimension. Just deal with the x. As for the duck on the left, tension is equal to ma. Done. As for the duck that's on the right-hand side, the force acting on the duck subtract tension is equal to ma, but this time the mass is 5 kilograms. You sub one equation to the next, and then you'll end up getting its acceleration. Sub the acceleration into equation number 1 because it's cleaner, and then you'll find out the corresponding tension. Well, what if friction was involved? Now you have to think about which way friction will travel. I think I have it animated out. All right, so if you're pulling the ducks towards the right, the force of friction will be towards the left. So now the formula for this is a bit more complicated because first off, you have to solve for your F net y. F net y, which will go to 0, is equal to Fn minus Fg. So Fn is equal to Fg, and Ff is equal to mu k times mg. Yes, you'll have to show this work. All right. Do I have it shown here? Yeah, just show your work for your force of friction at some point. As for the second object, you have the forward force of 10 newtons. So 10 newtons, subtract tension, subtract the force of friction, will equal your ma. Sub equation 1 into equation number 2, and you'll find out the acceleration has dropped quite significantly. If you recall from the previous slide, the acceleration was about 1.5 meters per second squared, and now the acceleration has dropped down to a third of the original value, all because of a 10% friction. Okay, and again, that's why we want to minimize our friction as much as possible in our devices. To calculate the tension, sub A most likely into equation number 1 because it's a whole lot cleaner. Let's say we get another duck and we add it to the chain. All right, you can imagine that for a problem like this, it's a whole lot more complicated in solving. That's fine. How about I give you a hint? All right, how would you solve this using the shortcut from tomorrow? Well, you'll notice that all these objects over here, they're all traveling in the same direction. And if they're all traveling in the same direction, then you know what, the outcome's going to be the same, especially if their force of frictions are all unified. So we could actually clump these all together and represent it by one big fat free body diagram. So 1 plus 5 plus 2 gives you 8 kilograms. All of these are being pulled with a total force of 10 newtons. If there's no friction, well, this problem becomes a whole lot more simpler because our free body diagram, yes, include the Fn and the Fg and what you're defining as positive. That's important for your FBD. But that's it for this version here. We see that our ma is equal to our F net, which is 10 newtons. So acceleration is equal to 10 newtons over 8.0 kilograms, which will give us 5 over 4 or 1.25 meters per second squared. Compare that with the answer key. Pretty neat, isn't it? All right, and we're going to see more of that shortcut in tomorrow's lesson. And you apply the same thing with question number 3, except this time around, just remember that you're pulling at a diagonal, and if you do the math initially, that diagonal force is not enough to lift up the 15 kilogram object, so it's not going to fly off into the sky. And luckily for us, since there's no friction involved, all we care about is just the horizontal component. So we find the force, which is 35.3 newtons, and we multiply it by the adjacent of 21 degrees. And you'll see that in the answer key. Okay. 35.3 times cosine of 21 degrees. That is our forward force. Subtract our tension number 1. Can you solve this using the simplified method I've shown you in number 2? Yeah, you could actually for this problem over here, because as I said, the vertical component does not affect the force of friction. So yes, you could simplify it. As for tension, sub it into equations 1 and 3, and then Bob's your uncle. That's about it. That's it for today's lesson and homework. Catch you in the next one.